Hello and welcome to the next installment of my Crafting Interpreters series. In this series, you're going to read the book Crafting Interpreters by Robert Nystrom. And in the previous two videos, we have read the introduction and we have started the work on the scanner, also known as a Lexer. And honestly, the YouTube algorithm is more pretentious than the Duolingo owl. You have to make videos every day or you will be cancelled. Therefore, I have decided to make a video today, even though it's past midnight. And let's go back to the code we have written in the previous video. So in the previous video, we have implemented these parts of what is written as Java in the original book. And maybe let's walk over the main function once again. So this main function initializes an instance of the interpreter. And then if the program is called with more than one additional command line argument, it displays the usage and exits with the exit code of 64. And if it's called with exactly one additional argument, because as we remember, argv at index 0 is the name of the program, then we run the script at index 1. And otherwise you run the REPL, which means you run the prompt that basically evaluates code in a loop. So at this point, the code does not compile because we have not fully implemented everything. And hopefully this is what we are going in this video. I think we got here after run prompt, we got the run function or the run method. And for now, it's just printing out tokens. And I think we also implemented the part with reporting errors. I think it was here. Yes. So we have the error interpreter, and yep, we had this. We had this. Okay. I think we got here. So here we have defined an enumeration type for token types, and technically Go doesn't really have enumeration types. Therefore, we implemented token type as an int with the first value starting as an iota, and then the rest is basically subsequent values for this given integer. Also, I have used the tool called stringer. I think so I have used the tool called stringer, and we used it to generate a string implementation, like a token type string implementation thing in here. And wait. So the thing is that since I have prefixed every value in this enum with token type, right now the implementation also prints token type before the name of each value. So I just found out that we can use the trim prefix option to try and trim the token type part. So maybe if I run it like this, stringer -type token type trim prefix token type, like so, then maybe in the string implementation it looks like this way. The stringer implementation is not going to include this token type thing. Also, this, no, not this browser. Copy link and this. Okay, so this tool I think can be used as a Go generate thing. So I'm going to copy this generator command and place it here. And I'm going to add this option, print prefix equals token type, like so, and type is going to be token type. And how can we run this Go generate thing then? So let's say I try to, if I deleted this file, can we run Go generate or something? Okay, so now if we run Go generate, then we get this stringer generation implemented for us. Great. So I'm going to go ahead and read the book. So for now we have just implemented the token type enum, and let's go to section 4.2.2. Literal value. There are lexemes for literal values, numbers and strings and the like. Since this scanner has to walk each character in the literal to correctly identify it, it can also convert a textual representation of a value to the living runtime object that will be used by the interpreter later. 4.2.3 Location information. Back when I was preaching the gospel about error handling, we saw that we need to tell users where errors occurred. Tracking that starts here. In our simple interpreter, we note only which line the token appears in, but more sophisticated implementations include the column and length too. We take all of this data and wrap it in a class. Okay, so we're going to create a type for a token. Okay, I think we already have a token struct or something. And now we also have an implementation for this token type. Okay. So I don't think anything happened here. So yep. Side note. Some token implementations store the location as two numbers. The offset from the beginning of the source file to the beginning of a lexeme and the length of a lexeme. I think we have read this. Okay. Now we have an object with enough structure to be useful for all of the later phases of the interpreter. 4.3 Regular languages and expressions. Now that we know what we are trying to produce, well, let's produce it. The core of the scanner is a loop. Starting at the first character of the source code, the scanner figures out what lexeme the character belongs to and consumes it and any following characters that are part of that lexeme. When it reaches the end of that lexeme, it emits a token. Then it loops back and does it again, starting from the very next character in the source code. It keeps doing that, eating characters and occasionally excreting tokens until it reaches the end of the input. Side note, Lexical analygator. Okay, well, this is weird. The part of the loop where we look at a handful of characters to figure out which kind of lexeme it matches may sound familiar. If you know regular expressions, you might consider defining a regex for each kind of lexeme and using those to match characters. For example, logs has the same rules as C for identifiers, variable names and the like. This regex matches one. If you did think of regular expressions, your intuition is a deep one. The rules that determine how a particular language groups characters into lexemes are called its lexical grammar. In logs, as in most programming languages, the rules of that grammar are simple enough for the language to be classified as a regular language. That's the same regular as in regular expressions. Side note, it pains me to gloss over the theory so much, especially when it's as interesting as I think the Chomsky hierarchy and finite state machines are. But the honest truth is other books cover this better than I could. Compilers, Principles, Techniques and Tools, universally known as the Dragon Book, is the canonical reference. Yep, so just for reference, this is the Dragon Book. Also, if you are new to this series, I have forgot to mention that you can find the whole book Crafting Interpreters at craftinginterpreters.com for free. Back to the text. You very precisely can recognize all the different lexemes for logs using regexes if you want to, and there is a pile of interesting theory underlying why that is and what it means. Tools like Lex or Flex are designed expressly to let you do this. Throw a handful of regexes at them, and they give you a complete scanner back. Since our goal is to understand how a scanner works, how a scanner does what it does, we won't be delegating that task. We are about handcrafted goods. Side note, Lex was created by Mike Lesk and Eric Schmidt. Yes, the same Eric Schmidt who was executive chairman of Google. I'm not saying programming languages are a surefire path to wealth and fame, but we can count at least one mega billionaire among us. 4.4. The scanner class. Without further ado, let's make ourselves a scanner. Create a new file called scanner. Okay, so this is a new class. I think it's still defined in the same package as in the same Java namespace. So I'm going to also create it in the main package. And then if things start becoming ugly, then I'm going to split this among different files. Okay, and side note, I know static imports are considered bad style by some, but they save me from having to sprinkle TokenType dot all over the scanner and parser. Forgive me, but every character counts in a book. Okay, I'm going to put it to the left on the left side, and I have to scroll down because it broke formatting, and we're here at scanner class, and I'm going to implement it in scanner.go, and we're going to define a type scanner struct, and it's going to start with a source. So this is going to be source, no, it's private source string, and tokens is going to be a list of pointers to tokens, I think. Okay, and now we define a new constructor. I'm just going to call it, no, I don't want ads at the moment. Sorry, Brave. New scanner with source as a string, returning a new scanner, or maybe it could even return a pointer to a scanner. Return new pointer to scanner with the source and an empty, source is going to be source, and tokens is going to be an empty slice, like so. Actually, I think we can even omit this because this is going to be the default value, right, like so. I know static imports are considered, we store the raw source code as a simple string, and we have a list ready to fill with tokens we're going to generate. The aforementioned loop that does that looks like this. Okay, so this is going to be a method on the scanner type, and it's probably going to be private, or maybe it's not. Let's see. I'm going to define it as private for now, and then we see if we need it to be public. So this is going to be for s is at end, and what's a start? I think we're going to find out pretty soon. S start equals S current. What's current? S scanToken. And this is going to be scanTokens. Okay. And S tokens equals append S tokens token, and it's going to be defined the token type equals TokenType EOF, and what's this? Lexim is an empty string, and literal is nil, and line is current line, I guess. I'm pretty sure this is going to be explained later on. This scanner works its way through the source code, adding tokens until it runs out of characters. Then it appends one final end of file token that isn't strictly needed, but it makes our parser a little cleaner. This loop depends on a couple of fields to keep track of where the scanner is in the source code. So I'm going to define a few more fields. It's start is an integer. Technically it could be an unsigned integer, but it probably doesn't matter. Current is also an integer, and line is an integer. Also, we need to start with 1. Since we are starting with 1 and not with 0, we need to define the line in the constructor. Great. The start and current fields are offsets that index into the string. The start field points to the first character in the lexeme being scanned, and current points at the character currently being considered. The line field tracks what source line current is on, so we can produce tokens that know their location. Then we have one little helper function that tells us if we've consumed all the characters. Private boolean is at end. Return current is greater than or equal to source length. Okay. I'm not sure if this is going to be enough, but let's hope. Sure enough, let's hope it is. Is at end returning a bool. Return S current is greater than or equal to S source length of source. Okay. Also, I'm pretty sure, so back when I was writing this in Rust, I think I just converted everything to use strings, because telling Rust, convincing Rust that your code is actually memory safe is a pain in the neck. But I think in Go, since it is a memory safe and garbage collected language, we could probably do just fine with slices. And I'm not exactly sure what type a slice of a source is. So let's say a source at 2 to 5. What is this type? Oh, it's also a string. Okay, so I guess we could just use a string. I'm not exactly sure if slicing a string returns a string reference to, a reference to the original string, or if it's just a copy. But either way, it probably won't really matter for the purposes of this project. Also, I'm not sure if those are I'm going to do some research and see if those are if modifying a slice of a string modifies the original string. 4.5 Recognizing lexemes. In each turn of the loop, we scan a single token. This is the real heart of the scanner. We'll start simple. Imagine if every lexeme were only a single character long. All you would need to do is consume the next character and pick a token type for it. Several lexemes are only a single character in logs, so let's start with those. Okay, so func as scanner scanToken, and C equals, I'm just going to call it C equals advance. And the advance is going to be a rune, I guess, as advance. Also going to call it, like, specifically define that this is a rune. Switch C case left brace. This is going to be s.add token token type left parent, like so. We don't need to break because breaking is the default behavior in Go. And I'm going ahead. This is going to be s add token token type right parent case left curly brace is going to be s add token token type left brace, like so. And there are 3, 6, 9, 10 tokens like this. So I'm going to go ahead and I'm going to put it in a single line. Hopefully this is legal Go. And I'm going to copy this and I'm going to paste it 2 more times. And I'm just going to replace those. Right now we have 9 lines, we need 10. So this is a comma, this is a dot, this is a minus, this is a plus, this is a semicolon, and this is a star or an asterisk. And I'm going to add more tokens in here. Token type right brace. This is going to be a comma, like so. This is going to be token dot. This is going to be token minus. This is going to be token plus, token semicolon, and token star, like so. And even though this was legal syntax, the Go formatter expanded it to be 2 lines. And also I think this is not going to compile because the switch is not exhaustive. So we're going to have to panic or do something else. Okay. And this is a side note, wondering why slash isn't here. Don't worry, we'll get to it. Again, we need a couple of helper methods. Private char advance. This is going to be func as scanner advance, returning a rune. And this is going to be return as source at as current plus plus. Okay, what does this return? I think we cannot really do it like this. We need to do it like so. Okay, source, well, let's byte as rune value. Oh. Okay, I'm pretty sure we're going to have to. I'm pretty sure we're going to have to split this into runes. And so I'm just going to make it into a rune slice, and this is going to be a rune slice, like so. And this way, indexing the source returns a rune and not a string. And then func scanner add token I'm just going to call it T because we cannot use type as an argument name because it is a registered keyword. So I'm going to just use TokenType. And oh shit, we can't use we cannot use it like so because the author uses a method overloading and it does not exist in Go. So we're going to define two different functions, and we're going to make a mental note of it. So I'm going to call add token with I think I'm just going to define add token with literal T, and this is going to be a nil, and define another method called scanner add token with literal T token type literal any, and text equals string source at s start up to s current, like so. What would this be? Yeah, this would be a list of runes, and then we can say tokens add tokens equals append tokens, and this will be a new token with type of T, lexeme being the text, and literal is going to be literal, and line is going to be the current line of the scanner. Okay. The advanced method consumes the next character in the source file and returns it. Where advanced is for input, add token is for output. It grabs the text of the current lexeme and creates a new token for it. We'll use the other overload to handle tokens with literal values soon. 4.5.1 Lexical errors. Before we get too far in, let's take a moment to think about errors at the lexical level. What happens if a user throws a source file containing some characters logs doesn't use, like hashtag or caret, at our interpreter? Right now those characters get silently discarded. They aren't used by the log's language, but that doesn't mean the interpreter can pretend they aren't there. Instead, we report an error. Okay. Also, this means we're going to need a reference to the virtual machine. I'm just going to use a pointer in here. I think this is kind of like interconnected, and we're going to get circular references pretty soon, cyclic references, or we could make it a global, like How is it? How was this actually built in this book? What's logs? Is error a static thing or what? Yeah, it's static. So it means it's like a class method, and there are no class methods in Go. So we're going to need to make it a global, I guess. And oh my. So I guess I'm just going to make it a global for now. Equals logs, like so. And yeah, I'm just going to rename it to VM, and I'm going to replace all the references. And then in here in scanner, we do not need the reference anymore. And again, this may be a mistake. Just for now, I'm going to do it like so. So if we encounter an unknown token, we report an error. Okay, yep. So default is going to be VM error, report error, S-line, unexpected character. Also, actually, this could probably be an error and not a string type, but for now, I'm just going to leave it like so. Because let's just try not to make too many deviations from the Java logic. Note that the erroneous character is still consumed by the earlier call to advance. That's important so that we don't get stuck in an infinite loop. Note also that we keep scanning. There may be other errors later in the program. It gives our user a better experience if we detect as many of those as possible in one go. Otherwise, they see one tiny error and fix it, only to have the next error appear, and so on. Syntax error whack-a-mole is no fun. Don't worry. Since head error gets set, we'll never try to execute any of the code, even though we keep going and scan the rest of it. The code reports each invalid character separately, so this shotguns the user with a blast of errors if they accidentally paste a big blob of weird text. Coalescing a run of invalid characters into a single error would give a nice user experience. 4.5.2 Operators. We have single character lexemes working, but that doesn't cover all of log's operators. What about bang? It's a single character, right? Sometimes, yes, but if the very next character is an equal sign, then we should instead create an equals bang lexeme. And note that the bang and equals are not two independent operators. You can't write bang space equals in logs and have it behave like an inequality operator. That's why we need to scan bang equals as a single lexeme. Likewise, less than, greater than, and equals can all be followed by equals to create the other equality and comparison operators. For all of these, we need to look at the second character. Okay, so case bang s add token, and there is no ternary operator in Go. So if s.match and s add token type bang equal, otherwise s add token token type bang, and case equals if s.match equals s adds token type equal, and else s add token type equal, and then case less than if s.match equal s add token. Wait, what? Oh, sorry. Add token type less equal, else s add token type less, and then case greater than if s match and equals s adds token type greater equal, otherwise s adds token token type greater. Okay, and we're probably going to have to implement this match method. So after scanToken, func scanner match expected rune, and this returns a boolean. So if s is at end, return false. If s source s current is different than expected, return false. S current plus plus, return true. Okay. Yeah, so as explained in the following paragraph, it's like a conditional advance. We only consume the current character if it's what we're looking for. So we're checking if we are at the end of the string. If we are, we return false. If the next character in the source code is not at current, and also current is pointing to the next character and not the one currently consumed, then we also return false. And if we are, and otherwise, it means we are at the correct rune, and we can increment current, and we return true. Back to the book. Using match, we recognize these lexemes in two stages. When we reach, for example, bang, we jump to its switch case. That means we know that the lexeme starts with a bang. Then we look at the next character to determine if we're on a bang equal or merely a bang. 4.6 Longer lexemes. We are still missing one operator, slash for division. That character needs a little special handling because comments begin with a slash too. And okay, so case slash if s match another slash, then we could basically just say consume comment, but whatever. For s peak is different than a new line, and s not is at end, s advance, and else we add token slash and back to the book. This is similar to the other two character operators, except that when we find a second slash, we don't end the token yet. Instead, we keep consuming characters until we reach the end of the line. This is our general strategy for handling longer lexemes. After we detect the beginning of one, we shunt over to some lexeme specific code. What does shunt mean? Also, fun thing, I set up shunt.
Shunt.
Shunt. Shunt something.
Shunt.
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 Shunt. Shunt something. To move a train or a coach of a train from one track to another. And what does it mean here? We shunt over to some lexeme specific code that keeps eating character until it sees the end. We've got another helper. And after much func scanner peak and returns a rune. If s is at end, return okay. Okay, I think we cannot do it here. The best we can do is return 0, and otherwise we return as source at as current. Okay, what was the condition again? Yeah, I think we'll be fine. And sort of like advanced but doesn't consume the character. This is called look ahead. Since it only looks at the current unconsumed character, we have one character of look ahead. The smaller this number is, generally the faster the scanner runs. The rules of the lexical grammar dictate how much look ahead we need. Fortunately, most languages in white use peak only one or two characters ahead. Technically, side note, technically much is doing look ahead too. Advance and peak are the fundamental operators and much combines them. Comments are lexemes, but they aren't meaningful and the parser doesn't want to deal with them. So when we reach the end of the comment, we don't call add token. When we loop back around to start the next lexeme, start gets reset and the comments lexeme disappears in a puff of smoke. While we're at it, now it's a good time to skip over those other meaningless characters, new lines and white space. Okay, case space form feed. What is it called? Form feed. I think it's called. I think we can just say break. Do we need to? Maybe we don't. Case new line. We increment the line. I don't think we actually have to print anything here. Yeah, I'm going to add a to-do in here. And if you encounter two slashes in a row, consume a comment until the end of the line, like so. When encountering white space, we simply go back to the beginning of the scan loop, that starts a new lexeme after every white space character. For new lines, we do the same thing, but we also increment the line counter. This is why we use peek to find a new line ending a comment instead of a match. We want that new line to get us here so we can update line. Our scanner is getting smarter. It can handle fairly freeform code like this. I mean, it cannot really do it now, but because it probably doesn't compile right now. Or does it? Nope. Main.go. What's in main.go? We can you can run new scanner with source tokens equals character scan tokens. Do we have scan tokens? We do have scan tokens. And why does scan tokens in the original? Well, okay. So scan tokens should return the I guess it should return the I think we just don't do it here and we just do it here. Scanner tokens like so. Does it compile now? Okay. Oh well. Index out of range 2 if linked to. And where was it? We are at how did you get? Okay, I think the next video is going to contain a lot of debugging, but where were we? I think we were here, and also maybe it's a good time to try and fix this. Oh, I think I know why this is. I think it's because the original was using the postfix version of a plus operator, and that should So we have to take the result first, then iterate it, and then return it like so, I guess. Yep, this seems to work. Okay, what about this? Okay, this returns nothing. And what about curly braces? Okay. Slash plus slash now equals. Okay. Pretty neat. Great, so I think this is a good time to commit. And we should also ignore the interpreter. I refuse to snapshot some files. Okay, good. Okay, great. And the next thing we're going to implement is the string literal. So if we encounter a double quote, we run the string, scan string, like so. Or maybe you could call it consume string. Yeah, I just use scanString for now. Find s scanner scanString, and for s peak is not equal s double quote, and s is not at the end, if s peak equals a new line, we increment the line number as advance. Okay. If s is at end, the head error, no, the report error, s line unterminated string. Yeah, like in the at some point later in the project, we're probably going to clean up the error reporting, and maybe, just maybe, we can somehow get rid of the static variable. I don't think I had a static variable in the Rust implementation, and but on the other hand, in Rust we could use associated functions on a type, and this does not work in Go. So let's see. If we are at end, we report unterminated string as advance, so consume the string literal, and value equals source s start plus 1 up to s current minus 1. And this is going to be a string, and this is s.source. And then we add token with literal, and this is going to be token type string with a literal of value. Okay. Like with comments, we consume characters until we hit the double quote that ends the string. Okay, let's see if we can actually get consume a string. Just say slash and hello world. Okay, I think we are currently consuming the string correctly, which is great. This is much easier than when with Rust, honestly. I remember with Rust, it was basically just trying to find the interpreter, like trying to convince the interpreter that my code will work. Back to the book. Like with comments, we consume characters until we hit the double quote that ends the string. We also gracefully handle running out of input before the string is closed, and report an error for that. For no particular reason, Lox supports multi-line strings. There are pros and cons to that, but prohibiting them was a bit more complex than allowing them, so I left them in. That does mean we also need to update line when we hit a new line inside a string. Finally, the last interesting bit is that when we create the token, we also produce the actual string value, but will be used later by the interpreter. Here, that conversion only requires a substring to strip off the surrounding quotes. In the case of Go, it's a slicing operator. If Lox supported escape sequences like new line, we'd unescape those here. 4.642, and I think this may be the last section we're going to do today. Number literals. All numbers in Lox are floating point at runtime, but both integer and decimal literals are supported. A number literal is a series of digits optionally followed by a dot and one or more trailing digits. Okay, this is going to be complicated. Since we look only for a digit to start a number, that means -1 to 3 is not a number literal. Instead, -1 to 3 is an expression that applies minus to the number literal 1 to 3. In practice, the result is the same, though it has one interesting edge case if we were to add method calls on numbers. Consider print -1 to 3.abs. This prints minus 1 to 3 because negation has lower precedence than method calls. We could fix that by making minus part of a number literal, but then consider this. This still produces -1 to 3, so now the language seems inconsistent. No matter what you do, some case ends up weird. 1 to 3, 4, 1 2.34. We don't allow a leading or trailing decimal point, so these are both invalid. We could easily support the former, but I left it out to keep things simple. The latter gets weird if we ever want to allow methods on numbers like 123.sqrt. To recognize the beginning of a number like seam, we look for any digit. It's kind of tedious to add cases for every decimal digit, so we'll stuff it in the default case instead. Okay, I guess. Does Go have an A? Is digit C? Okay, but if this is going to be Unicode, right? So I think this is going to be overkill for our purposes because the is digit thing, it's probably going to return the actual Unicode things. I'm going to open up the documentation and pkggo.dev Unicode. And example is okay, it doesn't say if we support all those weird digits, so maybe I can also go and see the source code. Oh yes, so this supports all those weird non-Latin digits, so I'm just going to use I'm just going to use the numerical values. If what do we call the talk is C? Okay, if C is greater than or equal to 0 and C is less than or equal to 9, we consume a number. Okay, I don't think number is a type, so we could just call it. I don't think number as is a reserved word, but since string is, I think I'm just going to call it scan number, like so, and we put this at the end. No, this is the receiver scan number, like so, and and this has to be an else. Okay. Oh, yeah, okay. This is a utility. I thought it was from the Java standard library, but it's actually not. So, and it's this here, this is defined as a method, but technically it could be it could just be a helper like this, right? C is greater than or equal to 0, and C is less than or equal to 9. And in here we could just use is digit C, like so. Does it work now? Okay, so this doesn't do anything because we have not implemented the scan number function. So, okay, I'm going to move this to the left, and this probably is going to break formatting again. Okay, good. For is digit as peak advanced. Yes, so we basically consume digits until we consume characters until we are sure they are digits, and okay, let's see if s.peak is a dot and is digit s.peak next. Okay, well, great. As advance, consume a dot, and for s is digit s.peak as advance. Okay, great. And I need to parse the number, so it's going to probably we're probably going to have to report it if we end up I'm going to mark it as a to-do, maybe. A parsing error if it occurs. Okay, number and error equals strconf. Was it strconf? Parse float. And yeah, like this. Text equals s source at s start up to s current, and then we parse the text as 64-bit float, and this returns the error. Okay, and also I have to parse it to I have to cast it to a string. Okay. If error is not nil, we report an error. To do use the built-in error interface instead of plain strings. Report error as line invalid a number literal. So I promise in the next video I'm going to modify the report error function to the report error method to use this thing, to use actual error things. Return Okay, s add token with literal, and this is going to be a token number with a number, like so. Okay, now let's see if this works. Pick next undefined. Okay, so func as scanner pick next, and this returns a rune. If s current plus 1 is greater than s in the length of s source, return 0, return s source at s current plus 1. Okay, can we parse it? Okay, we can parse number 20, which is nice. Can we pass 20.5? We can. Can we pass 2137.0? We can. Can we pass a 2137.0 in a string? We can. Okay, so this seems to be parsing correctly, and this is actually pretty impressive. And oh, actually we've passed the 1 hour mark, so I'm going to commit, and as usual you can find the source code from this video on GitHub. The link is going to be in the description below. The name is Karol Moros, and you have been watching Make Programming Fun Again. See you in the next video.